Okay, hi everyone. Thank you all for coming to the last session. So today we're just going to cover a bit of like actual CUDA programming, so writing your own kernels instead of using the higher level abstractions that we talked about on Tuesday. So we'll talk a little bit about what the CUDA programming model actually provides. So it gives you an abstract way of breaking a problem into smaller workloads, so partitioning some overall goal into smaller segments. And just like on the CPU, they call these threads as well. So this approach, they call it SIMT, so single instruction, multiple threads. But the sort of instruction or the program that each thread runs is called a kernel. And as programmers, if we're going to go to this sort of low-level kernel programming, we need to perform this partitioning ourselves manually. And basically, when we have these programs, what the program will do on each thread depends on like the index of the thread. So that's how you can coordinate work, is each kernel will get some label identifying which thread is currently running. So again, a kernel is just a program that runs on the GPU. And these sort of came about from like previously GPUs, including the name the graphics processing units, we used to basically compute some image on the screen, like what color each pixel was, and these were called pixel shaders. And they also had fragment shaders to do some sort of 3D geometry to render 3D scenes. And people essentially started using these shaders that were designed to render images to a screen to just do general compute. So they eventually changed the name just to use kernel instead of compute shader. So it was easier to understand. So this is a pretty simple example. So all we're doing to start with is to just create some arrays on the GPU. So this will basically just create 256 element arrays just with random numbers. So A and B, randomly generated arrays, and C is just some array to store the result of adding these two vectors together. And we saw last time that we could use a lot of generic Julia functions to actually work with these arrays, and that's because the CUDA array type, so if we say type of A is a CUDA array of float 32s. This CUDA array actually inherits from this abstract array class, which is used in base Julia everywhere for pretty much every function. So there are a lot of generic implementations in Julia that say that if you implement this abstract array interface, this code should be able to run. And the way you get your speed is if you have a specific type that has some special properties where you can accelerate that computation, it will use that type or define a new method with that type to sort of use these accelerations. The only problem is the CUDA array doesn't have exactly the same properties as a normal abstract array, so like a normal CPU array. And one thing that we saw last time is scalar indexing. It doesn't happen on the GPU, and so while it is implemented and you can use it, it's a lot slower because you're sending a request to get some information off the GPU, and that has to travel all the way back to the CPU. So if you imagine we have some custom function that just adds these functions together, adds these two arrays together and stores in a separate array with just a normal for loop. If we actually call this function and we've turned scalar indexing off, or if you're running it, if you're running Julia without the interactive mode, so like without the REPL, then you'll get an error saying that the scalar indexing is disallowed. So you'll have to do something else. What I would recommend, at least for this example, is to use the map functionality or just like broadcasting notation. But if your for loop is a bit more complicated and you can't sort of easily use like map, reduce, broadcast these functions, then you'll have to write your own kernel. So in order to do this, let's just go on to a new line and then write this exact same function, but instead of the abstract array type, we're going to specifically say that these are CUDA arrays. CUDA array and B is a.
Why do you have to specify?
Because these two functions will have the same name, and we basically want this to be the generic function, so this will work for any other type. But this will only run if your inputs are on the GPU, CUDA arrays. And so here we want to be launch this kernel, this CUDA program. So in order to actually write this kernel, we have to put it in another function. So I'm just going to call this myAdd kernel, and I'll have just the same inputs as before. So essentially what we want to do is calculate this element-wise sum, but we want to have one thread calculate one value in this array. And CUDA provides these functions that help identify which thread is running this specific code. So if you actually remember from the multi-threading course, there's a function called thread ID that identifies the current thread that you're running on. In CUDA, there is a similar thing, and it's just called thread IDX. And this is also a function as well. The indexing for these threads is actually three-dimensional, so they have an X, Y, and Z value, but if you're just doing things in one dimension, the Y and Z values will just be equal to 1. So for now, we're just going to ignore them, but we'll come back to it in a second. So then you'll have to do the index mapping yourself. So it supports up to 3D, maybe 4D on some newer cards, but 3D is your main one. With any amount of indexing, you can manually translate them yourself if you want more 4D. So this function doesn't have any for loops. It just has a calculation to get the current thread that's running this, and the addition itself and storing it into the C array. Also, one very important thing is CUDA kernels can't return any values. They have to just perform some operation in place. You can't return anything from it. So if you try and return a value that's not nothing, you'll get an error. Yes.
Why does it start with an underscore?
That's just naming convention. So this is a personal naming convention that I use for, I'm saying this is like a private method that a user of this code shouldn't use directly, only like the developer.
So I was thinking, but is it actually like private or?
No, Julia doesn't have any like hidden modifier stuff. Yeah, exactly. This is just something that I've taken from other languages. For now, I will remove it to make it a bit more clear. Yes?
I gets the index of which kernel will run the summation. Which thread in the GPU?
So we have to say how many threads we're launching, which we'll do next, and then.
No, I here. It's the index of each thread in the graphics card. Okay?
Yeah.
Okay. How many threads do we have? 10,000?
Yes. Well, that is a very important point of how many threads we have. But for now, we're just going to assume that you have as many threads as you want.
Yeah, but if you have a summation, a vector summation where the elements are more than the threads,
then you have to do something special. And we will come back to that, don't worry. I have some slides to explain it. So the way we actually launch this thread is we have to specify, we have to use this @CUDA macro, which will tell the compiler that this is launching some GPU code. And we have to provide it with the number of threads that you want to run this code with. So in this case, I'm just going to say launch as many threads as there are elements in the C array. I'm not doing any bounds checking to make sure that A, B, and C are the same size. I'm just leaving that out for clarity. So the first part is we just specify the number of threads we want to launch. And then the second part we will just call add kernel in the exact same way that you expect. And so what this will do is it will run this program on, in this case, 256 threads, and each one of those threads will set one element of the array. So if I add this code in, now if I run this, it will take a second to compile everything for the first time, but this should work.
Why do you have it in the same line? Length C, and then?
It's just the macro specifies the syntax of how you specify things. So these are keyword arguments. So you can,
Okay.
yeah, they're just keyword arguments. It's all in the documentation. Yeah, so what I should probably do is explicitly return nothing here, because this will return the actual reference to the kernel itself, which we don't want to do. So if we run that again, you'll see that it executed, there's no errors. And if we basically check that the addition is fine by transferring the arrays back to the CPU and doing the addition there, we can see that this implementation worked. But what you said before is, like, if we have arrays of different sizes, so let's say 2048, we'll just recreate all of the arrays and we'll try to run this operation again. And we get a very big error, and it's not actually clear as to what's actually happening here. So I'll tell you now, it's because there's only a limited amount of threads that we can launch in one go. So I'll go back to the slides.
So it's not very intuitive. I mean, it's coming from a for loop to this threads.
No, it's not. I should really clarify this.
For loop.
Yeah, you can write for loops inside, but that will just mean that each thread will perform that for loop itself, and so you're not actually parallelizing it. Yeah, kernel programming is hard. I should put that out there. It's very hard, and it's a very dense topic.
Mind-changing, you know.
Yeah, it takes a lot of time to get used to. There are huge books and 10-hour courses just on this topic. So this is only a sort of brief introduction to the topic.
Jamie,
Yes?
you said that you can initialize kernels, but gradually. You can't initialize 2048, but you can do 1000 and 1000 and 1000 in 3 goes, for example. What do you mean?
I will answer that, don't worry. So basically, like, why do we actually need to sort of segment these up into small chunks? Like, why can you only launch on most graphics cards? It's 1024 is your limit. Why can you actually do that? And it comes down to the diagram of, like, how these devices are actually built. So I showed a bit a different diagram last time, but this one sort of has stripped out a lot of the noise. So on the actual GPU, you have groups of processors called streaming multiprocessors. These are these SMs, and all of these SMs have access to the same sort of cache memory, this L2 cache, and sort of global memory, which is the memory on the device itself. Within each of these streaming multiprocessors, you have a series of streaming processors, which in turn have units for doing, like, floating point math, integer math. But most importantly is they have, within an SM, they also have a lower level of cache that's shared between the processors there. So these sort of blocks of threads can get mapped onto a single streaming multiprocessor, and the threads within these sort of blocks on those processors can have access to the same shared memory, instead of having to use the slower sort of global memory. So that's the reason you break these into blocks and threads, is there's like a physical hardware difference. Also, threads within a block are much easier to synchronize with each other. So if you need some synchronization behavior, like waiting for all threads to get to a certain execution point, it's much easier to stop a small block of threads instead of having to stop every single thread from all of the blocks across your entire GPU. But you can still communicate between, like, the different streaming multiprocessors by using, like, the global memory, and you can still synchronize between them, but it's slower because you have to stop everything instead of just locally stopping in one block. So hopefully that's not, well, that might not be too clear, but we'll sort of dive deeper and hopefully it'll make more sense. So we've already seen this. Each CUDA kernel has access to some labels, some indices that identify which thread is running. But that's not the full picture. We only looked at threads, but the CUDA programming model has grids, blocks, and threads. So each grid has a number of blocks associated with it, and within each block, you have a number of threads. And this is actually like a 3D indexing form, but if you're just working in 1D, you can assume that the Y and Z dimensions are just equal to 1. So just to go into an example, imagine you have an array with 8 elements here, and we want to segment it into 2 blocks. So each of these 2 blocks will have its own sort of unique set of thread IDs. So the thread IDs go from 1 to 4. So you only have 4 threads in each block, and it's sort of segmented over this over the 8 elements. We also have a block index, but for the first 4 elements in this array, the block index is the same. It's just 1, and then it's 2 for the last 4 elements. So we say that the block has a dimension of 4, and the grid, which is like everything in this case, has a dimension of 2 because you have 2 blocks in each. You have 2 blocks in the grid in that case. So the way you actually get the index from the block index and the thread index is by using this formula. Hopefully that is fairly straightforward. So each time you go into a new block, you have to add, or if you go into a new block, you have to add the block dimension times the block index to sort of offset the thread ID. We'll go over this in more detail. Equation, we'll put that back into our first CUDA kernel and actually see it working. So if we go back here, you see we still have the error of the number of threads was too high. So instead of just using the thread ID, we're just going to use that formula to get the block index. Again, in the extraction, we're just going to ignore Y and Z for now. Julia is 1 based, so we're just minusing 1 to sort of offset it. When you read CUDA examples online, if they're in C, that's all 0 based. So the one thing that's quite hard to translate between them is changing the indices from 0 based to 1 based.
So even in Julia, CUDA starts from 0.
Yeah. Unfortunately, yeah. So it's at least consistent when you're within Julia. So yeah, we can actually ask CUDA how many threads are in a given block using this block dim function as well. I should also specify these are exactly the same in C as well. They're called the same names. Yeah, that's why it's lowercase block, uppercase dim, which is not typical for the Julia naming convention. The only thing is I don't think it's a function call in C. So keep that in mind. So all we did was change the indexing to use this format. And now what we have to do is change the launch command to launch multiple blocks, not just threads. And the way we can calculate the number of blocks is by just dividing like the length of your input by the number of threads in a block. So in this case, I'm just going to hard code it to 1024.
Ceiling?
Yeah, so that's ceiling divide. So it's basically it ensures you have an integer coming out. So I will rerun these functions and hopefully, yeah, everything works as expected now. And if we do the test again, we can see it returns to true. So all we've done here is segmented it into blocks as well. And You can see if you sort of go back to the old example, when we had just 256 threads, even if you only have one block, this should work the same way as well. Yeah, so it works, no errors. But there is a slight issue. There's a slight issue here. So what would happen if I had 2050 instead? And anyone see any errors with this? It's okay if not. So if you have some,
Wouldn't you have 3 blocks?
you would have 3 blocks, exactly. So if you're segmenting into 3 blocks, like this, but your elements actually stop here. So only this part is your actual array. You're still going to launch all of these threads as well. So these threads over here won't have any work. I say won't have any work to do. We'll still try and perform this sum. The only difference is you're indexing past the end of the array. So what you should expect to happen if we run this again for these new inputs is a bunch of errors. And that's because you're accessing memory out of bounds. I think that's actually crashed the terminal, so try not to do this. What we have to do instead is add in a guard to basically say only perform this command if your index is in the right domain. So basically if I is less than or equal to the length of C. That basically just adds the bounds checking manually. If we might take a while to compile again, but this should solve the error and it should work fine. Also, don't worry too much about adding these guard statements in your kernel. I know if I said if statements are actually quite slow, but if you've already like parallelized the work, you have a lot of time being spent just scheduling the work. So once you're actually already there in the kernel, you can afford one if statement just to make sure everything works correctly. So yeah, this time we ran it and everything worked fine by just adding this guard statement. Okay, all right, so that's everything for the first example. I just want to talk a little bit about how it will extend into sort of multiple dimensions. So to sort of visualize this, you have the grid, which is like your overall program, or like the partitioning space of your entire program. And for now, we'll just assume 2 dimensions for the grid. This can have a Z dimension, but again, just imagine Z just has one element in. So each grid will contain multiple blocks. And each of these blocks will have an index in the X and the Y direction. So for example, this block 2, 3 will have a thread index X of 2 and a block index of 3 for the Y value. Then each of these blocks in turn will contain multiple threads. So I've done this in 2 so you can see. So this is like your sort of 3D diagram of the threads within one single block. And these will have an X, Y, and Z thread index as well.
Wait, so the grid is always 2D?
No, grid can be
Whatever.
3D, but you can set 2 dimensions equal to 1 and just pretend like there's only an X dimension.
Okay, grid maximum is 3D. Okay.
I think so. All of these values have an X, Y, and Z component to them. The reason why they have this is because, again, traditionally these devices were used for like graphics processing. So it might be natural to map, to easily map from like an image to a 2D kernel and a 2D partitioning space. If it's not natural for your application, you can just stick to 1D. So you only really have to use the other dimensions if it makes sense to you. Okay, yeah. So within each thread here, you have an X, Y, and Z direction. So I've sort of blown this up a bit, but imagine you have these 8 threads within a single block, and the thread indexes here go from 0 all the way to 7. I've made this 0 based on purpose. So the actual formula to work this out is pretty straightforward. And so you can see you just add on a dimension to the product each time you add a dimension into this. So if you're using, for example, dimension y of like 1, then this term, this dy, will go to 0. I say dimension. So if the y dimension is only 1 element and the z dimension is only 1 element, this y and z here will both be 0 for every element. So you'll only get the x index out. 0-based indexing, again, you'll see this in the CUDA.c API, but for Julia, when you want to transition to 1, you just offset the y and the z components here. So that's just a very sort of brief introduction. There is actually a cheat sheet online of like different indexing schemes and which formula you actually want that will combine the thread index plus the block index plus the grid index to sort of put it all together into a single index. Okay. And if you have to come back to this afterwards, all the slides will be online. So another thing that you might need to do in GPU programming is actually having access to some shared memory and also to perform some synchronization as well. Because some parallel operations are more complicated than just a one-to-one operation. So the only problem is once you introduce shared memory, you get into the issue of race conditions, which again is the same from the multi-threading lecture. And so you need some sort of inbuilt mechanisms to be able to synchronize your code to make sure that it's correct and you're not, you don't have any race conditions in your program. So I'll just go over a very quick example of reduction. We've seen this before, but I'll go over a very specific method because we're going to implement it with the GPU kernel. So again, imagine you have 8 elements here and you want to sum all of them together and you want to make use of the maximal amount of parallelization as you can. So one scheme of doing this is to add together like 1 and 5, add together 2 and 6, 3 and 7, 4 and 8. And you can do this in place, right? You can just overwrite the first 4 elements of your array. And here you can map each addition to a single thread. So the first thread will add 1 and 5, and then the last thread will add 4 and 8. And you can repeat this process until you only have 1 element left. So again, you split your list into 2 sections. You also have to synchronize here, but we'll come back to that. So you split your list into 2 sections, and then the first thread and the second thread will perform the 2 additions that you need to reduce the number of elements, and then, yeah, finally you have your last element overall. This works very well just because your input is a power of 2. If it's not a power of 2, you might need to add some additional code to actually make it generic and make it work. But we're just going to assume we're only dealing with power of 2 number of elements. At each step here, you had to synchronize first. So you had to wait until all 4 threads had finished on this first pass before you could start the second pass to avoid a race condition. So each of these steps needs some form of synchronization. I should also say the spacing between the elements that you add, so like 1 to 5, is half your number of elements, and then each time you're halving that spacing, again, which will come up in the code in a second. Okay, so we'll go to the example of estimating pi with the Monte Carlo strategy, but writing a CUDA kernel instead of hacking together the sort of high-level generic methods that we did on Tuesday. Yeah.
In the previous slide, you saw that addition on the GPU, right?
That was generic, right? It could be multi-threading, or it could be.
Because if it's addition, is it faster on the CPU?
If you have enough elements and you can parallelize enough things, yeah. I mean, the main thing is like the CPU will only have usually like 8 threads.
Yeah.
And so if you have an array that's like 2048 long, you can't launch 1024 threads, which is like half the number of your elements. Whereas on a GPU, you have that many threads, so you can parallelize a lot. Okay, so what I've done is taken the old method from that we used last time, which had to initialize some global memory on the GPU. Basically say, like throw a dart, luckily the diagram's still here, throw a dart at the board and check whether it's in the circle or out of the circle. And then finally use a reduce to estimate. And that worked fine, but we can do a little bit better by writing the kernel ourselves. So in order to do this, instead of defining some like global memory, what we're going to do is create some shared memory to store the sort of intermediate values, whether a dart is hit or not. So the way we create this shared memory is there is a nice macro CU static shared mem, which lets you create an array where you specify the type. For this, I'm going to use unsigned integers and only 16 bits, because later on we're going to be adding values together into it. That's why we're not going to use a bool, but this should be enough for our case. And then we want to specify the number of elements, but this shared memory is faster when it knows what size it's going to be at compile time. So I'm just going to set this value manually. There are ways in which you could make this dynamic depending on your problem, but for now I'm just going to hard code saying 256 values, and that's the number of threads I'm going to launch in a block as well. So that array will be available for all of the kernels later on. So all of the kernels will have access to that same array. So yeah, the first thing we're going to do is just copy the code to throw a dart, and I'm just going to store this value in a variable. And then we want to actually record this in the shared array. So we want to say, so we want to get the index of the current thread. So thread index, and then set that value in the shared array. And again, you have to be very careful when you're writing these arrays to make sure the typing all works. So I'm just going to be very explicit about what types, type conversions we're going to do. So this just converts from a Boolean value to an unsigned 16-bit integer. So up until this point, all of the arrays have run, but they might start and finish calculating at different times. So we need to make sure that all of the arrays have set their values in the array before we start reading and writing to that array to perform our reduction. So CUDA has a method called sync threads, which will basically wait at this line until all threads have reached that point in the execution. And when all threads have reached there, you can be sure that your hits array has been properly set. So the way we're going to do our reduction is we're going to start with a step size that's half the number of elements in our array. So here it's 256. And again, I'm using this div character to do integer division. So if it was like a 5 div 2, you would just get 2 out, not 2.5. And we're basically going to say, while the step size is greater than 0, or while it doesn't equal 0, we're going to loop and perform each step of this reduction. So the last thing we want to do is actually reduce the step size by a factor of 2 each time. So each time we perform a step, we reduce the step between the elements that we're adding together down by half. And we only want to perform this addition if the index is less than or equal to the step size. And the reason why we want to guard this is so if you're at the end of the array and you add on the step size to go to the end, you don't want to add elements outside of the end of your array. So again, this is shared memory, so we can just use the same array in place. We don't have to instantiate another array. And we'll say the hits value at the current index, well, basically equals itself plus the value at step size away from it. So hits at index plus step size. So in our array example, that was, for example, if you're on thread 1 and your step size is 4, you do 1 plus 4 and you get the value at that array at index 5. I'll simplify this code just to be plus equals. But what we want to do is we want to synchronize every time we perform each time we perform one step of this reduction. So each time we go down by a factor of 2 number of elements. So I'm just going to remove this sync thread line to the start of the while loop. So each time you reduce the step size, you synchronize first. Okay, so that is there. So at the end of this process on all the threads, the first value in the hits array will be the total of everything. And so the actual total itself will be in the first element of the hits array. And so what we want to do is sort of add this together with the counts from all of the other blocks as well. What I failed to leave out is I pass in some memory here, which is just an array with one element in, which has the count for every single block that you launch. So all of this reduction happens only within a single block, and now we want to add the results from each block together. And we only want to do this on the main thread, because we only want to add the total from each block once. So we just choose one thread to perform this addition. So what we can do is basically write to this memory like that. I will remove that variable there. The only problem here is we've introduced an issue here. So what's the issue that we've introduced if we're writing to this one location in memory from each block? If we're writing to the same piece of memory, writing and reading to the same piece of memory from different thread or different blocks. Yeah, there's a race condition as well. Fortunately, instead of having to do some synchronization across all of the blocks, just like in multi-threading, there is a macro for atomic as well. So this will make sure that any operation, anytime we access this memory, it's in an atomic fashion so that it will happen sequentially between blocks. And this will get rid of our race condition. So again, in the end, this returns nothing. The only thing is this global count variable will now have the total value inside. And so this was just the kernel, but we have to sort of wrap this kernel in a nicer API so that you don't have to write 10 variables every time you want to call it. So again, I've just hard coded the number of threads I want to launch as 256. There are better ways of writing this, but this is the easiest for me. So we can calculate the number of blocks just by dividing the number of samples we want to take by the number of threads that we're launching on each of the blocks. We also have to create some memory. So this array with one element just to store the total count. And again, you can just use like the CUDA API, CUDA.zeros. For this, I'm going to use a 32-bit integer, and I'm just going to store one value, or that array will just be of length 1. And now we want to actually run the kernel. So we want to run the kernel. And
the CLD just like take the ceiling.
yeah, so it stands for ceiling divide. It lowers to round, I think it's round up. That's how you would normally call it. That's how you can do like rounds. And for example, if you want to do floor divide, there's round down as well. That's quite hard to read. Well,
You know, like sometimes you get like floating errors, I guess, where it's like you do that, you do 6 divided by 3, but you do 2.0000, and then over 1 at the end. Will this put that to 3, or will it take it to?
Yeah, so basically the ceiling divide makes sure that if you do integers, you'll get an integer back. Whereas if you do sort of round,
You always get the correct, you know, it's not like 3 and it's 2.0001 or something. If you imagine more complicated numbers, it would go up to like from 2 to 3, right? Because it's technically greater.
I guess you use the ceiling divide or floor divide on integers, so you never actually convert it to a float at any point. It just gets rid of the remainder for you. Yeah, hopefully that makes sense.
Yeah.
Okay, so again, we've got our global memory. We've put that on the GPU already, but we have to launch the kernel. So we have to specify the number of blocks, the number of threads, and call the name of our kernel here, and pass in this memory, this total count. And once it's finished executing, we have to sort of take that memory and put it back on the CPU. So here, again, I'm being very explicit about types. You might not need this, but it helps to put types in and make sure your types are correct.
Is there a reason you use 32-bit and before you had 16? Or?
Yeah, so here I'm allocating memory on the GPU, and I know if I'm only doing 256-bit threads, the maximum value that's going to be stored in any one of those elements is 256, just adding up 1 that many times. And if you use 16 bits, that allocates less memory than if you were to use 32 bits or 64 bits.
Why do you use 32 now?
Later is because that will store the total count, and the max value of like 2 to the 16 minus 1 is only like 65,000 or something. So you can only put in a maximum n of like 65,000 before it will overflow. So you have to use a bigger range for the maximum total from all of your blocks. So again, you could play around with these and sort of maximize it any way you want, but this way I'm pretty sure works fine. So I'm leaving it there. So we want to get the array from the CPU, and we could just copy the array into an array from like on the CPU by using the array command. So for example, if you say array like total count, that will transfer it back to the CPU, but we only really want 1 value, so we can just use that scalar indexing. But we have to tell CUDA that it's okay in this case to use the scalar indexing, so we've only done it once. So I told you last time that there was a macro called allow scalar. So this begin end just says for these lines, allow scalar indexing. And I'm just going to overwrite this count variable with the array there. Again, if we're using just open close square brackets, this will index the first element of the array. So this is the same as writing like a 1 there. Yeah, and then finally we actually want to estimate pi, and again it's just 4 times this count divided by it would be n, but here we've launched but if n is not a multiple of 256, then we need to actually count how many additions we actually did. So in this case it's just the number of blocks times by the number of threads in each block. It's not quite n, so maybe it's a bit misleading, but it's less efficient to actually try and do less than n. It's more efficient to just launch more than you actually need and get a more accurate estimate.
Now you repair them? You're not calculating on the GPU, right?
No, so this is all on the CPU, and the CPU launches the kernel to start running. So this is like a wrapper around your GPU kernel launch to make it easier to use in the rest of your code.
Easier.
Yeah, easier is a relative term here. Also, since we've allocated some memory and we know we're not using it again, we can use this unsafe free command to basically let the GPU reclaim that memory. It's only one element, but it's usually good practice if you know you're not going to use it to clear it afterwards. So now let's see if this actually works. Yeah, okay, that's close enough to pi for me to be confident this is probably functional. But what we actually want to do is benchmark these. So these benchmarks might take a second to run. But
what is it, 2 to the 20 that you gave there? 2 to the 20 samples?
yeah, 2 to the 20 like darts that you throw, which is about 1 million darts.
Is it big enough to be, because I mean, the number of pi that we get, is the problem is even on the third digit. Is it good?
No, it's not a good method of calculating pi. Never use this for that, but if you're doing a Monte Carlo algorithm that's more complicated, maybe it's good enough.
Because I thought 2 to the 20 you will get something good enough, but
Yes, also the accuracy is tied to how good your random number generator is. Because every random number generator is pseudo-random and it's not going to be exactly uniform. There's going to be some bias towards some sections over another. So you've got to be really careful when you're using it to try and estimate some value that is very accurate. So yeah, all of the biases will come forward into your estimate as well. Okay.
There we go for like square root of dart.
Yeah. Yeah, so the error should be reduced by the square root of the number of darts, but that's only if your random number generator is perfect, which in most cases it's not.
But are you confident this is the random number generator and not the square root?
Yeah, I mean, you would expect if you did increase this to get a little bit better, but better in the average. I mean, like when you average over a lot of samples, but yeah, it's still not very good. I should point that out. It's not a very good estimator. Okay, so if we only care about the actual speed, here I'm just going to interpolate the value of 2 to the 20 instead of timing how long it takes to do that calculation as well. It probably would be negligible, but just to be consistent. So yeah, we'll let that benchmark run. This is using the GPU array, but sort of hacking together our implementation to use the broadcasting high-level API for CUDA. And this takes about sort of 54 microseconds, which is very fast. But now if we change to our sort of custom kernel, you would hope that we put in all of this effort to have a better value. And it is better, but only by a little bit. Okay. Okay, it's somewhat better. And you can basically make adaptations to this to make sure that it's that everything works the correct way. So one way in which you can check this is to make sure your code is type stable. So all of your like code, LLVM, warn type, all of that code is available, all of those macros are available for the device as well. So you can essentially run this on your code there, and you can see what values everything is. So for example, step size is using 64-bit integers, but GPUs are much better with 32-bit operations than 64-bit, which is why I tried to use.
why?
Why?
Why are they better? with 32?
For most graphics processing, you don't need 64 bits. 32 bits is more than enough. So they add on lots of 32-bit values instead of 32-bit like ALUs instead of the 64-bit versions, because that's what people use primarily.
It's more like space efficient.
Yeah, and they're more space efficient. So GPUs are quite often limited by their memory bandwidth. So if you can switch to 32 bits, you get twice the number of elements for the same amount of memory as 64-bit. So yeah, I'll make a few adjustments here. So for example, here, this is generating, so you see X and Y are 64-bit floats. So I'll change to 32 bits. You can see the step size is 64 bits. So here I'm going to just change that to 16-bit value instead. Well, I'll change that to int32 actually, because it's going to be added to index, which is an int32. And yeah, I think everything else should be fine. So if we run this again, hopefully if we do one type, so it says step size is either, oh, okay. All right. Yeah, sometimes it can be quite annoying to get this right. Okay, so everything is in 32-bit values, just to be sure. So if we benchmark again, hopefully we'll get something better than 50, which you should hope that we get something better than 50. Yeah, okay, that's much better. And what's actually better, I'll run this benchmark in the background as well. You also notice that the timings are quite tight as well. So there's only like a variation of a few microseconds, which again is the same here because we're using unsafe free. But if you're having to allocate memory, like globally on the device, you can get a huge slowdown by having to keep allocating these arrays again and again and again. Whereas here, you're only using like the local cache memory to allocate, which is much faster to clean up. Okay.
But the speed up is good.
Yeah, the speed is pretty good. You put in a lot of effort to these kernels. They might take quite a while to write and test, but sometimes it's worth it. Especially if your code uses this like hundreds and hundreds of times. If you can get a factor speed up of like 1.5, 2, it can save you a few days in computation if you're running your simulations long enough. Okay, so I'll leave it there for the actual examples themselves. As I said, this is a huge topic, and there are quite a lot of resources online. So NVIDIA has a book called CUDA by example, which is just lots and lots of code examples on practical problems of how to write these kernels. And it will introduce you to a lot of the concepts like the shared memory and more that we haven't actually spoken about today. All of the examples are in C, but most of the calls in C are almost one-to-one mapping with how you would call it in Julia. So the Julia documentation together with this book, it should be fine. It doesn't matter that it's in C. Again, just be careful of 0-based to 1-based. You have to be careful of that. Also, there is a very long workshop. It's just called GPU Programming in Julia. It has, or it's written or presented by 3 of the people that actually worked on CUDA.jl and most of the GPU packages available in the ecosystem. So they know what they're talking about much more than I do. So I would recommend that talk if you ever need to dive deeper into these topics. They also have quite a long section on using kernel abstraction. So that's how to write these kernels using this kernel abstraction package that will make your code portable. So you can run it on an NVIDIA graphics card or an AMD graphics card, or even just on your CPU as well. Also, if you need any questions, there is a whole dedicated section to GPU programming on the Julia discourse. So yeah, you will probably get help there if you're trying to write a kernel and you're getting errors. It's a great resource, and also on Slack as well, but I'd try discourse first before Slack. Okay, so yeah, this is the link for the final assignment. It's on the website if you want to access it there. But essentially, just like last time, it's just writing a kernel or some higher level GPU code to produce this sort of fractal image. It should be less work than the other weeks, I hope. But again, it's not assessed, so if you don't have time for it, don't worry. Also, if you don't have access to a GPU, don't worry. But yeah, that is completely everything. So thanks everyone for coming to the course. Thank you. Yeah, email me if you have any issues with anything. Yeah, have a good day, everyone. Thanks.